Test 1, 2. Welcome to the class. I'm not sure if you can hear me, but your mic is not switched on or not plugged in. There we go, Kutsu, I can see you. Sorry, is this a grade 12 class? Yes, sorry man. I am in the wrong grade 12 math. I don't have a screen for that. Can you hear me, Cleo and Kutso? Just give me an indication that you can actually hear me.
Yes, I can.
So this is, oh, I understand. We changed the times, didn't we?
Yes.
Okay. Right, excellent. Okay, just give me a second to set up a little page for us. Okay. Okay. Do you have an idea of what you're busy with at the moment?
Organic molecules. That's what I was busy with so far.
So this is physical science. Why is it not maths? Oh, it's physical science class. That's true. Sorry, I'm a bit confused with the days. So grade 12 physical science. Okay, good. Right. Okay, let's just do a quick review of where you are at the moment. We have completed momentum and impulse. Is that true?
Yes.
Okay, Cleo, you need to get a mic going. Somehow you have to like just give permission for your microphone to use Zoom. Oh, there we go. Your mic is there, but it's not, it's still muted. I'm just going to ask you to unmute the mic. There we go. Can you hear me, Cleo?
Yes, I can.
Wonderful. Okay. Sorry, I'm slightly confused this morning, I think. I thought we had a maths class for some other reason, but it's physical science.
Confused.
Pardon, I can't hear you.
I was also confused now when I saw the headings.
Yeah, sorry. What happened is the original mathematics grade 11 class was in this time slot, but we changed it. We swapped the classes around because that suits everyone better. So now we have a grade 12 class, but I was still thinking it was maths. No, it's physical science. So let's just make a quick list of what we've done this year. We have completed momentum and impulse.
Yes.
Great. Then we've also completed vertical projectile movement. Is that right, Kutso?
Yes.
Okay. So that's done, and then it's done. And then we've sort of touched on organic chemistry. But I'm not sure where we are at the moment. Because all we did, we just tried to do a couple of things that would help you in the test. But we didn't complete the whole chapter. So let's look at organic chemistry and let's just get an idea of what we should be able to do. Okay, so in our chapter on organic chemistry, remember this is a huge part of your syllabus. This is 50 out of the 150 marks in a chemistry paper. So there is the naming of the compounds, or naming of the molecules rather. That's name giving. And then we have intermolecular forces combined with physical properties. And in this section, you'll learn about isomers and stuff like that. And then we have reactions. So where do we feel comfortable at the moment? Can we name those molecules? Yes or no?
I'm okay with naming molecules, but then with the practicality of it, I'm not.
With the physical
sure.
properties.
Yeah.
Okay. Cleo, where are you?
I'm also fine with name. I'm basically the same.
Okay, so naming is sort of fine. I'll test you on the naming stuff. Okay, so we have to talk about intermolecular forces and also physical properties. And then you have reactions. You have addition reactions, substitution reactions, and elimination reactions. Plus, okay, those are the three important ones. Then you have polymerization, I'm not going to touch. That's just a little bit of studying. And you have combustion reaction. That is when you heat and it breaks up. It's also called cracking. These two, I'm not going to do. Because the amount of marks in the exam is so little, and it's basically flat box learning. It's just a piece of work that you have to learn. It's just theory. There's very little understanding there. Okay, so we're going to look at physical properties today, combined with intermolecular forces. It's not a difficult chapter. Okay, so let's look at the following. Remember, we have van der Waals forces. Can you remember this?
Yes.
Which one is the strongest van der Waals force?
Um,
Hydrogen bonding. Okay. Hydrogen bonding is the strongest van der Waals force. This occurs when a hydrogen atom bonds with either N, O, or F. So we call it hydrogen with NOF. NOF, N is what?
nitrogen.
Nitrogen, oxygen, and
Oxygen,
chlorine.
chlorine.
So when we have a hydrogen atom combined or binding with any one of those three atoms, then we have hydrogen bonding. Now, hydrogen bonding is a specific type of dipole-dipole bonding, but we just call it hydrogen bonding. So then we have dipole-dipole. That's the second strongest van der Waals force. And then we have dipole-induced dipole. You're not gonna see this much in any of your organic forces. And then you have London forces. It's basically these three that we're going to cover. The dipole-induced dipole forces rarely occurs in any organic molecule. Okay. Are you happy with that? Can you remember that?
Yes.
Good, so?
Yes, I can.
Good. Okay, let's go. So what they're aiming at is something like the following. You have like a beaker of, say, for instance, ethanol. There's H in there. Ethanol. And then you have a beaker of, say, for instance, we have hydrogen chloride. And I want to compare the boiling points. A boiling point comparison or a viscosity comparison or something like vapor pressure. Okay, let's talk about those things. What is boiling point? Remember, there's a very important definition that you have to learn there. Boiling point is when the vapor pressure equals the atmospheric pressure. That is a definition you'll have to learn, but okay, that doesn't make any sense. So boiling point basically means when a substance transforms from a liquid to a gas state. But if you give that as a definition, you get 0 marks. You'll have to learn the definition for boiling point from your textbook. But anyway, we understand it as when a molecule, when a liquid turns into a gas. So what happens when a liquid turns into a gas? The molecules that are bound with intermolecular forces, that intermolecular force is overcome and the molecules can freely move away from one another. So then it turns into a gas. Viscosity is what? That's just basically an index that gives you an idea of how easy something flows. So how easy does or how difficult, let's say rather how difficult it is for flow, the difficulty for flow. So something that has a high viscosity, like oil or honey or something like that, when you try and throw it out of the container, the flow rate's very slow. Well, if you compare it to something like alcohol or water or something, water flows much easier. So something with a high viscosity, a liquid with a high viscosity, does flow very difficult. And vapor pressure is just the pressure because of its evaporation. So any molecule or substance that vaporizes very quickly or turns into a gas very quickly has a high vapor pressure. So the higher the intermolecular force, the higher the boiling point. So a high intermolecular force will give a high boiling point. A high intermolecular force is directly proportional to a high viscosity. And a high intermolecular force is indirectly proportional to vapor pressure. So the higher the force, the lower the vapor pressure. That's very important. Okay, so now they want you to actually look at ethanol and hydrogen chloride. And they want to ask you, look, which one has the highest boiling point and why? 3 marks. So which one is the highest boiling point? Okay, how are we going to do that? Well, looking at the intermolecular force, the one with the highest intermolecular force will have the highest boiling point. So let's draw 2 ethanol molecules. So you see, there's ethanol and there's another ethanol molecule. Right, what type of intermolecular forces do we have? Well, we have London forces there. And between this hydrogen and the oxygen, there is 1 hydrogen bonding. Okay, so we have hydrogen bonding as our primary intermolecular force. There is also London forces, but they are negligent. Let's draw HCl molecule. Okay, let's make it something different because HCl is not organic. Let's change that into something like 2-chlorobutane. Right, let's write that. There's butane. Let's make it propane. I'm not sure about the 4 carbons. 2-chloropentane. So there's my Cl, and there's my other 2-chloropentane. Okay, so we have a polar molecule there. The difference between electronegativity between chlorine and carbon is huge, actually. So that's polar, that part. And this is also polar. I have London there and London there. So I have London forces. I'm just going to make it with L. And then I have dipole forces. So the primary intermolecular force in my 2-chloropropane is dipole. And the primary intermolecular force between my hydroxyl groups is hydrogen bonding. Okay, cool. Which one has the highest intermolecular force?
Hydrogen bonding.
Hydrogen bonding has the higher intermolecular force. And the dipole is also higher, but it's lower. Okay, now you have to answer this question. This is a 3-mark question. So we answer it the following way. 1 mark for naming or giving the answer. Let's start there. 1 mark for the answer. What is the answer? Which one has the higher boiling point? And the answer is? Ethanol. 2nd mark. Okay, let me 1 mark. The second mark is naming the intermolecular force or forces. Okay, so you're going to say ethanol has hydrogen bonding. I'm just going to write shorthand, okay, because my screen can't take all the info and you want to take a screenshot of. Do you understand that HB is hydrogen bonding?
Yes.
And what you can't write that in exam, eh? You have to write out hydrogen bonding. Are you with me, Kutso? Kutso.
Yes, can you?
Did you
No.
understand what I'm saying? You're not allowed to write HB for hydrogen bonding in the exam, okay? Are you happy? I'm struggling to hear you, Kutso.
Can you hear me now?
Yes. Are you aware that I'm just writing HB instead of hydrogen bonding, just shorthand?
Yes.
And what are you going to write in the exam?
Hydrogen bonding.
Yes. If you write HB, you're not going to get marks. I'm just using it as shorthand. So you can make notes of this or just take a screenshot. So it's nice and compact. And then you're going to name the intermolecular force at 2-chloropropane. 2-chloropropane has dipole-dipole forces. Dipole-dipole forces. And the hydrogen bonding is a higher intermolecular force. That is your second answer or second mark. Naming the intermolecular force, telling which one is the highest. Then the third part of the question is energy part. You get a mark for energy. Now, what you have to say is that therefore more energy is needed to overcome the hydrogen bonding. Therefore, it has a higher boiling point. So those are my 3 marks. I want you to quickly make notes of this, either do a proper screenshot or just make a note of this. I am going to be back in 1 minute, and then we're going to do exactly the same. There's 3 different scenarios. The first scenario we're setting up is where the molecules have different intermolecular forces. Just give me a second. I'm back in a minute. Just write that down, make notes. Okay, can we continue?
Yeah.
Yes.
Right, wonderful. Okay. So now we're going to compare something different. Say, for instance, let's say, I have just pentane. And I have, let's say, ethane. Right? Let's compare those two. I want to know which one has the, let's say, which one has the highest vapor pressure? Okay. Right. Remember when we work with intermolecular forces, you have to actually draw 2 molecules. So I'm going to draw pentane. Pent is 5. There's another pentane molecule. So there we have 1, 2, 3, 4, 5 areas of bonding. What type of bonds are those? Remember, they are actually between a carbon that's bound to hydrogens and another carbon that's bound to hydrogens. You can think of it as these are non-polar molecules. So all of these forces are London forces. Right. What about ethane? Ethane is just a 2-carbon chain. Are you aware of that?
Yes.
Yes.
Okay. So we have exactly the same intermolecular force, London. Right. So we can't distinguish between the two. The two intermolecular forces are exactly the same. So what makes the difference here is the fact that pentane is a longer chain, which gives us a broader or a bigger area or surface at which bonding can take place. So this surface area consists of 5 carbons, while this surface area consists only of 2 carbons. So there's 2 London areas that London forces can operate in ethane, and there's 5 areas in pentane. Okay, so which one will we need more energy to break the bonds? Pent or ethane or pentane?
Painting.
Pentane. Okay, so which one has the highest vapor pressure? Well, the one with the lowest intermolecular force will give the highest vapor pressure. It will what? It will turn into a gas much easier, so it will turn into vapor much easier. So I'll say that ethane, there's my first answer, ethane has a higher vapor pressure, 1 mark. Then I'm going to refer to the intermolecular forces. I'm going to say both have London forces. But what? The surface area of pentane allows for what? For a what? The surface area. Okay, let's just answer it the other way around. Might be easier. Pentane has a longer chain. Therefore, more surface area, or a bigger surface area would probably be better to say. Let's say a bigger surface area. Therefore, it has a bigger area for bonding. Okay. Therefore, what? More energy be required to overcome the pentane bonds. So 4 marks, because the 2 intermolecular forces are the same. 1 mark to give the answer. 1 mark to refer to the intermolecular forces. Additional mark that we didn't have in the previous one. 2. Now that the forces are the same, they are not the reason. So I have to bring in another reason. And we have a longer chain which gives us a bigger area for bonding. I think your book may say surface area. And then you have more energy required. So that's 4 marks. Write that down or just set that up for you. Can you actually hear me well?
Yes, I can.
Yes. Yeah, we
My
can.
computer is telling me I can have better sound somehow. Okay, tell me when you are ready.
I'm ready.
Can continue.
Can I continue? Okay, cool. Right, now we're going to compare something else. So this is the second one. There's about 4 things we have to compare. Let's say that we have, let's say we have 2-methyl propane, and we have butane. What's interesting here, I'm going to draw those molecules. There is CCC prop chain, and then on 2, there's a methyl group. Would you be able to draw this?
Yes.
Now, what's interesting about these two molecules, I'll show you now. If I compare them, I'm not going to put the hydrogens in. You have to put the hydrogens in, really. Don't. Those hydrogens I'm not putting in just to make it easier to draw. So there's my one, it's going to use yellow. There's my 1,2-methyl propane molecule. There's my other 2-methyl propane molecule. So I have C4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. So that's the molecular mass, C4H10. Now, butane looks like this. I have 4 carbons in the chain. And then there's another 4 carbons in the chain. The molecular mass of each butane is also C4H10. So if I compare the molecular mass of both of these molecules, they're exactly the same. So there's my one butane, and there's my other butane molecule. Right. All I actually want to know from you is which one will require more energy to break up the forces than which one will require more energy, do you think? The green one or the yellow one?
Green one. I'd say the green.
Okay, right. You are right. But let's start off. What intermolecular forces do we have here in the green one? London. It's London forces. Remember, there's no polarity here. There's no hydrogen bonding. You only have to worry about hydrogen bonding. So you either just looking for N, O, or F. I don't have any N, O's, or F's there, so it's not hydrogen bonding. And you have to worry about polar molecules. I don't have any polarity here. They're all just carbons and hydrogens, so this can be non-polar. So we have London forces at the butane, and the only forces we have in the 2-methyl propane is also London forces. So again, my intermolecular forces are exactly the same. So even though we have to mention the type of intermolecular force, that's not the determining factor. So what is determining the amount of energy needed to break the one yellow molecule away from the other yellow, or the one green from the other green? It is surface area again. Look at my 2-methyl. So, okay, the answer is which one, let's make up a question. Which one has the highest viscosity? Okay. The one with the highest intermolecular force will have the highest viscosity. Why? The stronger the molecules are bound to one another, the more difficult they will slip over one another to flow. Right, look at my green, my yellow 2-methyl propane molecules. Okay, because of the spheric nature of this molecule and the spheric nature of that molecule, the surface area between them in which bonding can take place is less. Then look at the butane molecules. They are linear or flat, so the surface area between them in which bonding can take place is higher. It's like trying to, if you've got some wood and glue, if you take 2 planks that are squared or flat and you glue them together, they will glue much stronger than if you have 2 round objects trying to be glued together. The 2 round objects only have a small surface in which you can put the glue and connect them to one another. And that surface, there's always under a lot of tension. You can easily break those 2 things away from one another. It's like trying to glue 2 balls to one another. This is a small area where you can actually put the glue. So let's start. The first question is the answer. Which one is the highest viscosity? The answer is butane. The butane, why? Okay. Both have London forces. So I've given I get 1 mark for the answer. I get 1 mark for telling giving the intermolecular force. So I'll just give you a better answer there. Both London forces is too simplified. I'm just going to give you a better answer. The intermolecular force at both molecules is London forces. Okay, so I'm just naming what type of force it is, and I'm telling you what force it is. So that's a mark. Then I'm going to give the reason. So the intermolecular force is not the reason because they got both the same intermolecular force. So I'm going to say that the butane molecule, butane, is more linear and therefore have a higher surface area, while the 2-methyl propane is spheric and has less surface area or area for bonding. Mark. Therefore, last is always energy. More energy is required to overcome butane. Fourth mark. I'm giving you very shorthand now. I can actually, you can actually just follow the steps in your textbook. Your textbook will give you like a longer answer. Not a longer answer, just give the answer, not shorthanded. All I'm trying to do is I'm trying to give you a visual reference of what it looks like. So when you see these molecules, you remember these purple parts showing the surface area, and then you'll know the answer. All you need to do is learn how the answer must be structured. The answer is structured firstly by giving an answer, secondly by referring to the intermolecular forces. If they are the same, you incorporate another part that will give you an extra mark by giving you another reason except intermolecular forces. It's either surface area or molecular mass or something like that, and then you refer to energy for the 4th mark. So when the intermolecular forces are the same, it's 4 marks, and when they're not the same, it's 3 marks. Last one. So now I'm going to compare, let's say, 1 chloropropane with 1 bromopropane. Right, there we go. Prop with a chlorine, another prop with a chlorine, prop with bromine, propane with bromine on 1. Cool. Right, let's look at the intermolecular forces. Then we'll answer the questions. I have London force there, London force there. I have a polar molecule there. I have a polar molecule there. So this is dipole, dipole. I have London forces there, London forces there, polar, polar. So dipole, dipole. So the intermolecular forces are exactly the same again. So let's say, which one has the highest boiling point? Which one has the highest boiling point? Right. Can you actually give me the answer? Who of you can give me the answer and the reason? Okay. Right. So let's go. The answer is 1 bromo propane. Okay. So that's the answer. Then I have to look at the intermolecular forces. So both has dipole, dipole. So the intermolecular force is not the reason why 1-bromopropane has a higher boiling point, but I get an answer, a mark for giving the intermolecular forces. Third, there must be another reason, and that is because the bromine atom has a higher what? Molecular mass. It has a higher molecular mass. What does that mean? Basically, it is a bigger atom. So I'm going to draw something to explain that. This is my carbon bounded to that chlorine. Then on this side, I have a carbon bound to a bromine. Now, the atom looks like this. Something like this. Or the molecule looks like that. And the bromine one look like that. Bromine has got what? 35 electrons. Chlorine only has 17 electrons. What does that mean? There's a much bigger area in bromine that 35 electrons can move in. So in other words, all 35 electrons can actually move to one side of the molecule. That makes this one side of the molecule really negative and the carbon side positive. So this is called a dipole moment. It's a small moment in time where a lot of electrons is moving to the one side of the molecule. Remember, bromine has a higher electron negativity than carbon, so that it draws all the electrons towards towards the bromine atom. So I can have a huge negative side compared to chlorine, which only has 17 electrons. So it's also negative there, but it's less negative than the bromine compared to the carbon. So the higher molecular mass will give me a higher dipole moment. Do you understand that? Dipole moment means that moment in time where your polarity is higher than normal. Okay, so what they want is higher molecular mass. Bromine atom has a higher molecular mass. Last, therefore, more energy is required. To what? To overcome the bonds in my 1-bromopropane. And more energy, therefore it's a higher boiling point. Did this somehow make sense?
Yes.
Okay, so we've done 4 things. The first one was comparing different intermolecular forces. Then you just go on the chart. Hydrogen bonding is the highest, so that will be the highest energy needed. Second one, dipole second, and London is third. So you just go in that sequence. Then the third one is both intermolecular forces are the same, but the one chain is longer than the other one. So the longer chain gives a bigger surface area, so more energy is required to break the longer chain. Then we have 2 molecules that's got the same molecular mass, but the one is spheric and the other one is linear. More energy is required to break up the linear one because there's a bigger surface area. And then we have 2 molecules, they're exactly the same. They've got the same chain length, got the same bondings. The only difference is the one atom bound to the chain has a higher molecular mass, and that gives a higher dipole moment. And so that one needs more energy. So the bromopropane needs more energy. So it will have a higher boiling point, higher viscosity, but a less vapor pressure. And this is basically this section in this chapter. It's also not an awful lot of marks in the exam. The chemical reactions or the organic reactions is huge. It's a lot of marks, and the naming is a lot of marks. So what I want to do now, maybe we must just screenshot this or take a note. I can also get you some notes on this. If you're struggling with intermolecular forces, I can actually get you notes on this. All right. What I want to do, I want to test you on a couple of names. Is that okay?
Yeah.
It must be okay. Right, so what I'm going to do, I'm going to paste a couple of molecules on the screen, and I want you to copy them. And after you've copied them, you're going to name it. And then we're going to compare notes. Just give me a minute to get to those ones. All right, let's see what's happening here. If your screen goes dark, it's just me copying stuff. So whenever I copy something, your screen will just blank out for a minute. So there's no sweat. Okay, there's the first one. Copy that quickly and name it. I'm going to paste another one. Sorry. Can you see it? It's going to go dark again for a minute, for a second. Okay, there's two molecules. You're going to copy both of them and just name them. And I'll show you how to do names again. Those are easy ones, or relatively easy. And you can just put up your hand. There's a little blue hand you can put up if you're finished. Okay, do you have names? Okay, I'm going to show you how to get the names. Right, get the longest chain first. I'm going to number it. 1, 2, 3, 4, 5. Is that correct? But I can also number it 1, 2, 3, 4, 5. So there's two ways of numbering the chain, from left to right or right to left. So the rule is that alkyl halides and normal substituents have the same priority. Are you with me,
Yes.
Cleo?
Yes.
They have the same priority. So I need to look at the numbering system which gives the combination of those two the smallest possible values. So if I look at the red numbers, it gives them a combination of 3 and 4. Well, if I look at the blue numbers, the combination is 2 and 3. 2 and 3 is 5, and 3 and 4 is 7. So the red numbers are wrong. Right. Now, you don't name something, you build a name. So we build the name as follow. You have 5 carbons, and they are single bonded. 5 is what? Pent.
Pentane.
So that's pentane. Then on carbon 3, we have a fluoro group. And on carbon 2, we have a methyl group. Now you're going to name that alphabetically. And F is before M in the alphabet. So I have 3 fluoro, 2 methyl pentane. Did you get that? I really hope you've got it right, eh? I'm not going to ask now. Okay, now let's do the second one. Again, I have 1, 2, 3, 4, 5 carbons in my longest possible chain. Or I can use blue numbering. Again, normal substituents or alkyl substituents and group 7 or halides have the same value. So the red numbering is a 1. The blue numbering is number 2 plus 3 plus 5, which is 10. And the red numbering is 1, 3, 4, which is less than 10. So the red numbers are the right ones because they give my substituents the lowest possible value. Okay, I have again pentane, 5 carbons. I have on carbon 1, chloro. Then on carbon 3, I have a methyl group, that is single carbon. And then on 4, I have another methyl group. So let's use alphabet. Chloro is first. 1, chloro. Then look at this. Because there's 2 methyl groups, I do 3, 4 dimethyl. Di means 2. And pentane. Boom. Happy?
Yes.
Okay. Let's continue with the naming. Okay, I need to get, I'll do alcohols later. So I just want to get double bonds going. Just going to do first just a warm-up one, the easier one. I'm not putting in the hydrogens, okay? That's an easy one. Right, there we go. You can write down the structure. When you write down the structure, okay, then we all put the hydrogens in because you have to. Quickly write that structure and try and name it. you have an answer? Come. It is because you do not know this work well enough yet. Okay. And this is like considered to be free marks once you've learned how to build names. Okay. I need to get you to a place where you do all the work in your textbook so that you actually have questions on this. Good, so. Do you have a name?
I'm still at copying. I still got the copying. Let me see.
Okay, let's number 1, 2, 3, 4, 5, or blue. 1, 2, 3, 4, 5. Right, now, the red numbers gives the double bond the lowest possible value. Can you see that? Everyone.
Yeah.
The red numbers gives a 2 to the double bond, while the blue numbers, the lowest value attached to the double bond is a number 3. So the blue numbers are out. Okay, now look carefully. I'm building a name. 5 carbons is pent, but there's a double bond, so it will be pentene. It will end in ENE. But you also have to tell me on which carbon the double bond is, and it's on carbon number 2. So it's pent 2-ene. Happy?
Yeah.
No, you're not happy yet. You should be able to do these. You need to go and do revision on them. Okay, very important. We cannot slip up. This is very important work. It's considered to be free marks in exam because the chemistry you're going to do the rest of the year is much harder than this. Okay, now another rule they're testing here is the following. I'm going to number it 1, 2, 3, 4, and the question is which has priority, the double bond or the halide? The double bond has priority. So therefore the double bond needs to get the lowest value, meaning the red numbers are wrong because it gives the double bond higher values. So let's build a name. It's got 4 carbons, which means what? But it's butene on carbon 1. Also on carbon 3, there is a bromo group. So I have 3 bromo. What? But 2-ene, 1-ene. I don't need that hyphen. 3 bromo but /1/ene. You can also write it on the old numeric system. It's still corrected. 2 bromo 1 butene. But that's the old IUPAC naming. I'll rather use the new one if I was you. So it's 3 bromo but 1-ene. I'm going to give you another one on your own. This naming is going to take a while to get the naming if you are still struggling. Because alcohols and there's carboxylic acids, there's a lot of naming to be done. Right. Dot down that one and try and name it. Tell me if you have a name. Quickly dot that down, see what you can do. Okay, let's number red. 1, 2, 3, 4, 5. Or blue. 1, 2, 3, 4, 5. The red numbers win because it gives the double bond, which has priority over the substituents, the lowest value. I'm deleting the blue numbers. This is how we do it. You take your pencil, you number from left to right and right to left, or you search the longest chain, you number it in 2 ways. Then you choose the right numbering. So we have 5, which is pent, but it's a double bond, so it's pentene. On carbon 2, the double bond is, so it's pentuene. Then on carbon 5, I have a chloro group. Also on carbon 2, I have a methyl group. Naming is given alphabetically, so 5 chloro is first, then 2 methyl second, and then we have pentuene.
Wait, why 5 chloro?
5 chloro is first, not because of the number, but because C is before M in the alphabet.
Oh, okay.
So we name alphabetically, not numerically. So the chloro will always be before the C will always be before the M, just because in the alphabet C is before M. Look, this is something they chose. There's no reason to do that. They could have just done it numerically, but they chose alphabetically. Okay, let's just do basic alcohol naming because we don't have a lot of time. Just test you there. I want to see if you can actually dot down that alcohol. I want you to answer me if it's primary, secondary, or tertiary alcohol, and I want you to give its name. So is it a primary, is it a secondary, or a tertiary alcohol? Let's choose them, and I want the name. I'm going to do another alcohol at the bottom, which you should also be able to do. Okay, the top one. Let's go. 1, 2, 3, 4. I'm not going to bother any other way of numbering it because that gives the hydroxyl group the lowest possible value. Hydroxyl has got high priority. It has priority over double bonds and triple bonds as well. So I have 4 carbons, which means but. But it's an alcohol, so it ends in all. Also, there are only single bonds, so it's actually butane, not just but. So it's butane alcohol, and the hydroxyl group is number 2. We chop off the E for pronunciation reasons. So that's butane 2-ol. Very important. You chop off the E at the end in alcohols and also in carboxylic acids. Also, number 2, it's another alcohol. So I'm numbering it in a way that the hydroxyl group has the lowest value. 1, 2, 3, 4. It's again but with single bonds. So it's butane alcohol. The hydroxyl group is on carbon 2 again. But there's also a methyl group on carbon 2. So I have 2-methyl. Let's give that name. 2-methyl chop off the E, butane 2-ol. The red one, the top one, is a secondary alcohol. Secondary. Why? The carbon attached to the hydroxyl group is only attached to 2 other carbons, while the carbon attached to the hydroxyl group in the bottom one is attached to 3 other carbons. That makes this tertiary. So this is a tertiary alcohol, that's a secondary alcohol. It's just some theory that you have to learn. Okay, so your lesson time is going to be on Thursday mornings, 10:30 to 11:30. If I don't get any questions from you because of the work you're doing, then I know you're not working hard enough. All right. What is difficult for a homeschooler is to actually know how hard you should work. Remember, any student in grade 12 that's got physical science as a subject, they have class every day. So basically, and they get homework. So basically, the minimum time you're spending on physical science every day is about 1 hour and 15 minutes, nothing less. Every day, at least 1 hour and 15 minutes, you're doing physical science. You're either doing work or studying. Somehow you have to fit that in. And this hour we just done now counts for half of it. You should put in another half an hour today somewhere in physical science, at least. Okay. Cool. I'll see you next week this time for physical science.
Okay.
Bye-bye. This lesson is recorded, so I will make it available on YouTube. You just know where to search for it. If you don't know, then you must WhatsApp me. I'll give you a link.
Okay. Thank you.
Bye. Bye, Kutso.
Bye.